What's up guys, welcome to another video of the course Dynamic Programming for Beginners. This is part 8 and today we are going to learn how to reconstruct the optimal solution of a problem solved with dynamic programming. First of all, let's answer the question, what does it mean to reconstruct the optimal solution? Well, the idea is pretty simple. Let's recall the previous lecture in which we solved the paid staircase problem. In that problem, we had to minimize cost and then print out the minimum price we had to pay to reach the top of a staircase. So that's great. We were able to answer the question. But the problem is that we still don't know what are the actual steps we need to take in order to get to the top. We know that the price we have to pay is, let's say, $8. But what is the actual path? Whom do we even pay this $8 to? So this is what reconstructing the optimal solution means. When you solve optimization problems, oftentimes you will want to print out the steps that led you to the solution. It could be the shortest path to a destination, or it could be the actions you had to take to minimize profit, and so on. So today I will show you two things. First, I will show you how to reconstruct the solution to the paid staircase problem. And second, you're gonna love it, I will show you the general approach, the framework, so to speak, that will help you to solve, that will help you to reconstruct the solution of a pretty much any optimization problem that was solved with dynamic programming. All right, now let's try to solve the paid staircase problem in order to illustrate how to reconstruct the best solution, right? The optimal solution. So I'm going to solve the paid staircase problem for when n equals to 8, meaning that we have 8 stairs. And then we also have, you're allowed to make either 1 or 2 steps at a time. So k equals to 2. Now I'm going to draw the staircase 0, 0 meaning we are on the ground, first step, second step, third step, fourth step, fifth step, sixth, 7, and the last one is 8, right? And now we also want to add prices, the price that you have to pay in order to step on each stair, right? Let's say the first one is 3, 2, 4, 6, I don't know, 1, $5, and the last one is $3. So these are the prices that you have to pay in order to step on a certain stair, right? Now, next, I would love to recall the transition function for this problem. Check out the previous video if you haven't seen it to understand why the transition function is like that, but the transition function for this problem is f of n equals the minimum between f of n minus 1 and f of n minus 2 plus the price to step on the nth stair plus p of n, right? And then p in this case is all of these numbers. It's an array of all of these prices. So we have p here, which is an array of 0, 0 meaning the first, when you are on the ground, you don't have to pay anything, right? So 0, 3, 2, 4, and so on. You got the point, right? Okay, cool. So now let's actually try to solve this problem, right? I'm going to use this sort of like a table here, and we will solve this problem for every single step, for every single sub-problem. So this is I, this is our sub-problems, and then f of I is the answer. Okay, so 0, so first staircase, right? When we are on the ground, how many what's the minimum cost we have to pay to get to the top? It's just, we don't have to pay anything, right? So the answer is 0, according to this transition function as well. Now, when we are on the first step, when we want to get to the first step, what's the minimum cost we have, what the minimum price we have to pay to get to the top? So it's $3, right? We have to pay $3. Now, here is the thing. When we solve all of this sub-problems, I'm going to use red marker and write down where we came from, what was the sort of like best previous step in order to get to the current stair, right? So to get to the first step, previously we were on the ground, right? So that's what I'm going to say. We were on the ground, 0. Now, second step, right? To get to the second step, we could, like if we apply the transition function, it's the minimum between the previous two plus 2, right? In this case, plus p of 2. So the minimum between 0 and 1 is 0, right? So we say 0 plus, like according to the transition function, minimum between this guy and that guy plus p of n, right? So 0 is the minimum, 0 is the minimum plus p of n, 2. So 0 plus 2 is 2. And then where we came from, it's essentially where the minimum was, in which point was the minimum. So the minimum was in 0, right? So that's what I'm going to say here as well. So the minimum was in 0. Okay, so now f of 3, right? F of 3, it's the minimum between the two, the previous two. Between 1 and 2, the minimum is 2, plus f of 3, p of 3 is 4, so 2 plus 4 is 6, and the minimum was in 2, right? The minimum was in 2. So we solved this guy, we solved that guy, we also solved f of 2, and we solved f of 3, and now we need to solve f of 4. Okay, so f of 4, the minimum between these two guys is 2, plus p of 4 plus 6 is 8. Okay, 8, and the minimum was in 2, right? So we say 2. We came from 2. Now, f of 5. F of 5 is the minimum between 3 and 4 is 6. 6 plus p of 5 is 7. 6 plus this guy, 7. And the minimum was in 3. Okay, f of 6. F of 6 is the minimum, like if we apply this formula again, the minimum between 4 and 5, right? n minus 1 and n minus 2 is 7. So 7 plus 1, 8. And the minimum was in 5. 5. Now, f of 7, so we have 7 and then 8. F of 7 is the minimum between 5 and 6 is 7. 7 plus 5 is 12. And the minimum was in 5. And the last one, f of 8, is the minimum between 6 and 7. It's this 8. So 8 plus 3 is 11. And the minimum was in, and the minimum, so this is 11, and the minimum was in 6. Awesome, so we have the solution to this problem, and we also have basically sort of like a path, a reverse path, so to speak, of where we came from, right? So when we were on the last step, we came from 6. When we were on the 6th step, we came from 5. So now we can do it, now we can reconstruct the optimal solution by going through all of these red numbers, red values, and essentially writing down the solution, the optimal solution, the path, sorry. So I'm gonna say path, and the first element in this path is essentially the last state of the problem. So where we were at the very end. At the very end, we were here, right? On the last step. So we say, okay, so the first one is 8. Now, here, to the last step, right, we got from 6, right? Because we recorded it here. So 6. So we go to 6 and we write down, we say 6, okay, to the last step we got from 6. When we were in the 6th step, we came here from 5, because it says here 5. When we were in the 5th step, we came from 3. So we go to the 3rd step. On the 3rd step, we came from the 2nd step. And then on the 2nd step, we came from the ground, from 0. And this is essentially the optimal solution to this problem. It's just in the reverse order because the problem is sort of like we have to make all of the steps first in order to sort of like know what is the best path, right? And this is what usually will happen to you as well. So you will have this path in the reverse order. Now, like if you want to print it out like that, it's possible. You can also just reverse it and print it out correctly, but this is pretty much it. Now let's try to code it up, and then the next thing is I'm going to show you the general approach, the framework, so to speak, on how to reconstruct pretty much any solution to a problem that was solved with dynamic programming. Alright guys, so I've got the paid staircase 2 problem here. The only difference between this one and the paid staircase problem is that now we need to return the cheapest path to the top of the staircase, right? So in the previous one, we had to return the amount, the cheapest price to get to the top, the minimum price to get to the top. Now we have to return the actual path, that would, allow us to get to the top, the cheapest one. So immediately one change that we can make here is that we no longer return the amount, we return the array, right? So we need to return indices of the staircase, or like just the staircase indices that we need to take in order to get to the top. Now, as we said during the whiteboarding session, we want to record the previous step, right? So every time we step on a certain stair, we want to know where we came from and what was where we came from. So in order to preserve all of these values, we're going to create, an array of the same size as dp. So we'll say just array of integers n plus 1. And every time we apply the transition function, we want to say where we came from. So when we step on the ith stair, right, we can get there either from I minus 1 or I minus 2. So if dp of I minus 1 is less than dp of I minus 2, it means that we came from I minus 1, right? So if this guy is less than that guy, then we came from I minus 1, from the previous step. If dp of I minus 2 is less than I minus 1, then we came from the step before the previous. So basically, we can say if dp of I minus 1 is less than dp of I minus 2, then we came from the previous step. Otherwise, we came from the one before the previous. So now we know where we came from, and we have all these values, right? And we can use these values in order to reconstruct the path. So let's create a path array, and now we want to populate this array with values from the from variable, right? So the very last step, the very last state, was the very last step. So we can start a loop and we say current equals to n. The reason why current equals to n is because we want to access the last element of this from array, right? And the last element is nth element, because this loop is running from I to n, including n, right? When we access from of current, we will get the value, if you remember from the whiteboarding session, the red value on the last step, right? Now, while current exists, right, while we can access current, we need to get, we basically need to say current equals from of current. Basically we follow the pointer, so to speaking. So now we have the current, and we can populate current we can append current to the path. We can push it to the path, onto the path. So we can say path equals append path current, right? So if you remember from the whiteboarding session, we had something like, I don't remember those answers, but like 3, we came from 2, and then like 4, we came from 1, and then the last one was 11, right? We came from, let's say, 6, whatever. So current here are these values, right? 6, 1, 2, and so on. And each next iteration, we want to kind of like follow the pointer. So if this is 6, then we want to say, okay, follow the 6 and then go somewhere, like go to the index 6, right? So this is why the code looks like that. Awesome. And then the very last step here is, so let me actually show it to you. I think it's a little hard to explain. So now we can return the path, right? Let's run the test cases. So I have the test case from the whiteboard. Okay, so the test case failed, right? So first of all, as you can see, the expected path, it looks like 0, 2, 3, 5, 6, 8, right? But what we got back is 8, 6, 5, 3, 2, right? So first of all, the path is reversed, right? And the second of all, we don't have this 0, right? It's missing. So the reason why is it's reversed is because we go from backwards, right? We reconstruct the path, and this is something we already mentioned. We always reconstruct backwards because we have to, in order to kind of like calculate the best path, we have to first go through it, right? And then once we go through the path, we can actually go back and reconstruct it, which is why we always have to reverse. But the other thing, the reason why 0 is missing is because of this condition here. So somehow we need to stop reconstructing the path, right, at some point. And there are a few options here. So the first option is basically we can just have like while current is greater than 0, right? So when we hit the ground, then we need to stop looping. So that's exactly what is happening right now. So once we get to the ground, to the 0th step, so to speaking, it's not a step, but just to the ground, then we can start the loop and stop the loop. And in order to have the 0th value in the path, we would just manually need to add it, right? So we would have to say something like path appends path 0, right? And this would work. The other approach is we could say while current is greater or equals to 0, and then we always append the path, we always append current, but then we can say something like if current equals to 0, so if we reach the ground, then break. This will also work. Okay, cool. So now let's run the test and see if things make sense. Okay, so we have, as you can see, 8, 6, 5, 3, 2, 0, and then 0, 2, 3, 5, 6, 8, so they're reversed. And the last basically thing we need to do here is to reverse the path. Unfortunately, Go doesn't have a function to reverse the path, the array. So I'm going to quickly write it, reverse. So we accept numbers. It's a shame that Go doesn't have one, right? So we want to start from the beginning, and we also want to keep track of the last. So we're going to do it in one loop. Nums1, while I is less than j, we want to do I plus 1 and j minus 1, right? And now we just simply want to swap the two. So we'll say ij equals ji. And now we can just return nums. Awesome. And now instead of returning path, we can just return path reversed. Let's see. Now I'm going to run the test. Boom, the test has passed. Awesome. So this is pretty much it, guys. Now, the last bit is I want to show you how to reconstruct the path for other problems. So the framework that you can follow is actually outlined here, but the general idea is that, I'm going to use this comment section, is that you would have some path, array, or it could be like anything, really any data structure, but some path, right? Some data structure. And then you would need to reconstruct it by following the following code. So you have your current variable that would represent the best sort of like last state, right? And then in our case, the best last state is when we got to the top of the staircase. It was n, right? Now, while current exists, we want to say current, we want to follow the pointer, right? We want to say current equals source, or like from, of current. And then we also want to say path push dot current, and then return path dot, let's say, reverse. So something along these lines, but this is essentially the template that you can use in order to reconstruct the path for pretty much any optimization problem that was solved with dynamic programming. So you start with the best last state while current exists. You need to, while the current exists, you push current to the path, and then you follow the pointer, which is, points to the previous state. And all those previous states store it in the from variable. That's pretty much it, guys, for today. Thank you so much. This one was a little long video, but hopefully, it was helpful. Enjoy the rest of your day. Take care, and I'll see you next Sunday. Bye.